Okay, guys, welcome to Comp 9418. I'm Gustavo Batista, the lecturer in charge. So I hope that you enjoy the course. We're going to discuss different probabilistic graphical models during the course. I really like this idea of probabilistic graphical models. I think they are very clever ways of putting together computer science and statistics. The idea is that we can bring the formalism of statistics and we can bring the algorithms for computer science and put these two things together in order to make inference to a large number of variables. So we're interested in domains where we have, I don't know, hundreds or maybe thousands of different things that we need to measure about the world and reason about it. So we're going to cover different graphical models during the course. At the end of this presentation, I will show you a small list of some of the graphical models that we're going to discuss. We will probably recognize a few names, and we're going to study those models in details during the course. So the idea of this first lecture is not to give you a full understanding of graphical models. It's more to give you a little bit of the motivation why these methods were proposed, and also to understand a little bit of the context, right? So it's going to be like a little bit of a history. What was going on in artificial intelligence when the first researchers proposed to use probability as a way of managing reasoning, right? So as a way of doing reasoning. And it was a quite long pathway because research in artificial intelligence, they believed that people did not think using probabilities, so why probability should be the way of making inference? Probably something that's closer to how we think should be better. And in the initial stages of artificial intelligence, people were really committed in creating something that was truly intelligent and were really committed to the idea of using those techniques that in some way resemble the human reasoning in the artificial intelligence systems. So you're going to be, in this first class, going to be a sort of an overview where I'm going to touch different topics and have an initial understanding of how these probabilistic graphical models work. We're going to provide one example using Bayesian networks. That's one type of probabilistic graphical model. And don't worry too much if you don't get all the details, as we will cover these topics in further details as we move on in the course. And it all started with automated reasoning systems. And the idea here is that we can create a system that can take conclusions about the world by making some observations. And to make it a little bit more concrete, let's suppose that we want to diagnose a certain disease. So we find a physician that is an expert in that disease, and we make an interview. We try to take from his mind what are the rules that he uses in order to make a diagnosis for that disease. That will be our knowledge base. And we need also an inference engine. The inference engine will work with the knowledge base. We will take some observations from the world that will be the symptoms that we are observing in a patient and make the conclusions that it is the diagnosis. So this is the general idea of automated reasoning. In order to do that, we need to have something that links these two blocks, and this will be a certain representation language. And the representation language needs to be powerful enough so we can represent the concepts that we need. At the same time, it must be able to be interpreted by the inference engine so we can make the inferences. This is a very powerful idea that is still very influential until these days. And it was proposed by John McCarthy, that was a very clever researcher in artificial intelligence that back in 1959 came with this idea that we can separate the knowledge base from the inference engine. And it is powerful because the knowledge base will be dependent of the problem that we have at hand, but the inference engine is general. As far as we have this link that is the representation language that connects these two parts, the inference engine can be reused in several different problems as far as we can represent the knowledge base of these different problems in the same language. So this idea is very powerful. So it's so powerful that it created a new area of research that's called knowledge-based systems or model-based systems. There is a problem here that when John McCarthy he proposed this idea back in 1959, he committed with logic as being the language to represent the knowledge base. And deductive logic would be the inference engine for this language. He later revised this idea and it opened a little bit so other forms of representations can be used. But the problem with logic is mostly because the logic that they had at that time were called monotonic. And the monotonic logic is something like this in a very simple way. It's an inference mode that you can only add knowledge to your knowledge base. It's incremental in the sense that you can only grow that thing up. You cannot revise it. We cannot remove things that you learned. And that is a very strong commitment because in the real world, we're going to observe things. We're going to learn about the world. And we need to revise what we learned. We need to remove something that we learned, but now it's not correct anymore. So the important thing here is that we can use the same idea with Bayesian networks or in general with probabilistic graphical models. So we just use as representation language the graphical model and we use the laws of probabilities to make inference. So what is this idea of monotonic logic? Is, as I said, it's like having an inference system that you can only add stuff to your knowledge base. You cannot remove it, so you cannot revise something that you learned in the past. And it is a very strong assumption because in the real world, as we observe new things, we may need to revise what we learned before in order to make it more up to date. So in a little bit more formal way, the definition would be like this. Suppose that we have a knowledge base delta that logically implies a conclusion alpha. If we learn some new thing, and I'm calling this new thing gamma here, if we add gamma to the delta, it will also imply the same conclusion alpha. So alpha is still truth, even though we learn some new thing that is gamma. We cannot fuse alpha with new knowledge. And that is a very strong assumption. So let's try to make it a little bit more concrete with a very simple toy example. Let's suppose that we have this rule that if a bird is normal, it will fly. And we have an autonomous car. And we'll try to draw this car the best I can. All right, and this car is moving towards this little bird here, right? So this little guy. So if we have a purely logical reasoning system, this car we're going to stop for every possible bird that we see on the road because we don't know if the bird is normal or not. We are seeing this bird for the first time. So we're going to stop for every bird. So we have to make some assumption, and this assumption must be something very logical, something, well, we know that most birds are normal, so we can think that is our knowledge base, and we can add something that we call an assumption that every bird is normal, right? It's an assumption, it's not true, but it will make the system work. And if every bird is normal, so now this rule is going to fly because we see a bird and we assume that it's normal, so it will fly. So now we have the opposite. We have something like the car will not stop for any bird if it is normal or not. So we will have a problem because as we move towards the bird, we may look at it and say, okay, this bird looks wounded. So it might be hurt and not fly. So it might be better to stop the car. right? And we may have some additional rules here in our knowledge base, like something if the bird is wounded, it will not fly, right? So, and in this case, we start to approach the bird, we see that it's wounded, and we're going to fire the second rule, and we will have one conflict, because the first rule is saying the bird can fly, and the second one is saying the bird cannot fly at the same time. So that is what we call an inconsistency, right? You see, we are getting problems. What we can do, and that is what was proposed for non-monotonic logics, something, well, these assumptions can be retracted. So we're going to separate the knowledge base in two parts. One are the things that we know, the facts, and the second one are the assumptions, things that we don't know but we assume to be true. And we're going to keep those assumptions as long as we can, as far as we don't get in any inconsistencies. If we get into an inconsistency, we're going to remove the assumption that's causing inconsistency, and we're going to solve the problem. It sounds simple, but it's not. So, of course, this is a very simple example. So, in this case, we know that this assumption here is causing the problem. Assume that every bird is normal. We're going to remove it. So, we're going to not fire the first rule anymore. We're going to remove this, and now we know the bird is not a flying bird. We're going to stop the car before hitting the bird. Okay, sounds simple. But imagine that you have hundreds or maybe thousands of different rules in your knowledge base. You have dozens, maybe hundreds of assumptions, and we will have to manage all those rules and assumptions at the same time in a dynamic way, because as we move our car, we make new assumptions, we make new observations about the world, and we derive new conclusions. So at some point, we'll have something that's really messy. We see an inconsistency in our base. We have to revise our assumptions. We remove then, typically, the criteria for doing that. We remove the assumptions that are causing inconsistency. I'm going to keep all the other assumptions. So we try to have some methods that solves the inconsistency. But when you remove an assumption, we want to make some other rules not to fire anymore. We have to revise the base, remove some of the conclusions that we had before. It will be really messy. In practice, we learned that this is a problem that's a lot more challenging than it sounds to be. And with time, we're starting looking for other ways of doing the same thing. Instead of using non-monotonic logic, instead of using assumptions, try to use a different way of representing these assumptions. And the way that we're going to use in this course is associating what we call a degree of belief. Degree of belief is simply a number that we're going to assign to our propositions in a way that we can revise those numbers with time as we observe the world. And we're going to work in a much easier way. So let's suppose that we start, and I'm going to use the symbols for probabilities like a P, even though this degree of beliefs do not need to be probabilities. We're going to see in the next slide that there are other concepts that also are used to express uncertainty. But let's suppose that we are not certain if the bird can fly or not. So we say something like this. The probability of that little guy here being a flying bird is initially, as I don't know anything about this guy, is going to be something like 0.99. So I'm pretty confident that it will be a flying bird. Why? Because most birds can fly. And so assume that that one will fly too. So you continue driving the car and assume that the bird will fly by itself and will not need to slow down the car in order to not kill the bird. But as the time passes, we're going to make some observations, and we can change this probability. In a very natural way, this probability can go up or down, and we will update data. We don't need to have any sort of assumption. So this is what we call the prior probability. It's something that we assume prior to knowing anything, any more details about the problem. But later on, we can have what we call a posterior probability, that will be the probability of this little guy flying, given that I observed that it is wounded. The bird is wounded. Okay. So now I have an observation, and this comes here in the form of a conditional probability. So we call this the posterior because it's something that is a probability that I'm computing after observing something about the bird. And given that it's wounded, I would say that it drops to 0.4. So this first, the prior, can be larger, can be much larger than the posterior. Actually, it can be smaller too, it can be equal. I don't know. But the important thing here is that it can change over time. And we can make more observations, and we can say, okay, the probability of being a flying bird, given that it's wooden, and it's a chicken, okay, that is 0, 1. So it will not fly at all. So we can update that as we observe more, as we get closer to the bird and learn more about it in a very natural way. Okay, so this is the idea of degree of belief, right? So the degree of belief is simply a number, and we assign a number to each proposition that we have in our knowledge base. It's a way of replacing this idea of assumptions. Instead of assuming that something is true or false, we're going to have a more soft way of having those assumptions. I will not say that it's a flying bird, it's not a flying bird, it's normal or not normal. I will assign a probability of this bird being normal. And we can base these probabilities, for instance, based on frequencies. Oh, I have observed most birds are flying birds, most birds are normal, so I'm going to say that the prior probability for a flying bird is 0.99. So this is going to be a number, and with these numbers, we're going to use what we call probability calculus to derive some conclusions. So I assume the bird is normal with 99% probability. So the probability of the bird being normal, I will say that's 0.99, and I use probability calculus. In some way, I compute that the probability of being a flying bird is also very high, something like 0.9. So this is the inference that I'm going to do, right? So based on some probabilities that I have, some degrees of belief that I have, I will derive some conclusions that will also have a degree of belief. And based on the conclusions, I will take some decisions like stop the car or continue or so on. It's important to say that probabilities are not the only way of expressing degree of belief. There are other ways of doing that. Researching in artificial intelligence try different ways of expressing degrees of belief. One classical example that is very well known is called fuzzy logic. The central idea is different from probabilities. In fuzzy logic, we have what we call the degree of membership. So a variable can be member of different sets with different degrees of membership. We will not get into detail, of course. For this course, we will focus on probability as a way of encoding those degrees of belief. Something that is always important that I mentioned before is that we can update those probabilities upwards or downwards as we learn about the problem. So we can start with 99% probability and lower down to 20% probability as we learned something about the word. So a final word about this is that those probabilities are numbers, and they are numbers in a certain range, like between 0 and 1, or in a different interpretations between 0 and The important thing here is that we use these numbers, it's a convention between a certain range, so we can make these probabilities comparable between them, right? So it's merely a convention, a sort of a normalization idea that all probabilities will stay in a certain range, so it's going to be easier to compare events with different probabilities. Finally, before we close this video, we must think that in order to make a final decision, the probabilities will not suffice. We need something extra, what we call a decision theory. So we can think that, okay, I know that is the probability of being a flying bird, and I want to create a rule that's something like, if this probability is smaller than a certain threshold X here, then we need to stop the car. And you may ask, what is that X? Should it be 0.5? I don't know. Should it be 0.2? Maybe we are so concerned about the birds. Killing a bird will be bad to the image of our company, so we should be extra careful. I don't know. Actually, there is a way of thinking about this. And I'm going to use a very simple example to illustrate the general idea, and we'll come back to those decision graphs at the end of this course. But the central idea is that in order to make the final decision, we need to have some extra information about the problem. And we will put together the probability with that extra information in order to make a final decision. This decision theory typically converts the probability together with this extra information into what we call an utility function, right? So we will convert to a utility. Usually that utility is expressed as a monetary value because it's easier for us to interpret, but it doesn't need to be that way. But as a monetary value, we think about money, it may help us to interpret the problem in a simpler way, instead of looking in abstract numbers. So to make this idea a little bit more concrete, let's suppose that we want to capture the bird, right? So it's not a very ecological example. And the bird costs, or it's worth $40. And we have two methods. One, the first method, it costs $30. But it's guaranteed to capture the bird. So we have two different options. There is a first method and a second method. The first method is guaranteed to capture the bird, but it's a little bit more expensive. So it's going to be $40 minus the $30 equal to $10. So that will be our profit for the first method. For the second method, it's a little bit more complicated. It is cheaper. So it costs $10, so we have a larger profit. It's going to be $30, but it works differently. For non-flying birds, it may capture, it captures for sure, and it is a flying bird. It only captures with 25% probability. So it is a flying bird, so right here, fly, and not flying. It is a flying bird. I have just 25% probability of capturing. If it is a non-flying, I have 100. So what's going on here, right? As we have just one chance in 4 in capturing the bird, so we're not making $30 profit here. We have to multiply this 25 by the $30, and on average we will have something like $7.5 profit, right? Because we are not capturing every bird that we try, we're just capturing one every 4. So let's suppose that it costs $30. So on average, we will, if we repeat this experiment for a large number of times, on average we will have a profit of 7.5, right? On the other side is a not flying bird, so it's going to be 100 times $30 will be $30. Okay, now we know a little bit more of how to take this decision. And in summary, if we observe the bird, make all the observations, put in our inference system, and if this inference system tells us that it is not a flying bird, we know that we should use the second method, because as it's not a flying bird, it will capture the bird for sure and give us a profit of $30. If the probabilities increase towards the bird being a flying bird, there will be a moment that these two methods here break even. But as we go up and we are more certain that it is a flying bird, the first method becomes more attractive because it gives us a profit of $10 for sure instead of 7.5 on average. So we'll move toward the first method. If we are sure that it's a flying bird, I selected the first method. So what I'm trying to tell you here is that we can compute the probabilities, but for several problems, that is not the final step. We will need an additional step when we put this information of probability together with a decision theory in order to support the decision theory. And decision theory is not something more than another kind of a graph where we put together the details about the problem and we make a final decision. All right, so I think that it is a good moment for us to have a break. So I invite you to stretch your legs, grab a coffee, and we will continue in a second video. See you soon.